Hello. Good afternoon, class.
Good afternoon, Doctor.
Okay. How many people have we got now? I cannot count. Never mind. Okay. So let's start the class now. Okay. The rest they will join when they join. Can you see my slide? Column design.
Can.
Okay. Good. Great. Okay. Right. So for today, it's going to be mainly just theoretical stuff. And then maybe tomorrow we will tackle the actual calculation and design. Okay. So we will only so I will go through the just the theoretical stuff with you today. Okay. Base and I will follow this slide as a base, as a template. Okay. So we are going so this is obviously the next topic. So we've done flexural design, we've done shear design, and then we've done a bit of slab design. So now we will look into column design. So column design is different. Okay, it's inherently different from what we've done previously, flexural, shear, because it's not really governed by flexure, and it's not really governed by shear. Yeah. So column design, it's governed by a mix of axial load and flexure. Okay, working together. So there's a bit of balancing act to be done there. Okay. So you will notice that as I go through the presentation today. Okay. So column design. Okay. So first of all, I'll start off with what is a column, in case you don't know what a column is. You should know. You are in your third year. You should know, but I cannot make that assumption. Dangerous assumption. Okay. So what is a column? All right. So if you're sitting on a chair and you've got a table in front of you, if you look at the table, the legs of the table are the columns supporting the table. Okay, so I always like to use the table analogy. Yeah, when I try to describe how a slab works, I use the table analogy juga. Yeah, I ask you to look at the table. Okay, so same thing for a column. All right, the column is basically the legs of the table. Okay, so when you have a building frame, it's basically the vertical members lah. Okay, so if you look at the graphics here, let me see if I can conteng. Boleh ke saya conteng? Okay. Oops. No. All right, never mind. Here, this thing here. Okay. So this is your typical building frame. Okay. So if as I've explained earlier, okay, you the element that directly supports your weight when you enter a building. Okay, so when you enter a building, the element that directly supports your weight is actually the slab. That slab has to transfer your load to the beams. The beams then transfer the load to the column. All right, down to the foundation. Okay. So a column is primarily a compression member. Yeah. So because it's carrying a load, it's a compression. Okay. However, a column may also need to resist bending. In other words, flexure. Okay, in other words, flexure. Bending and flexure means the same. I mentioned this before. All right. So these two forces work together. The compression and the bending, they work together. Sometimes they help each other. Sometimes they help each other, but sometimes they make the situation worse. Okay. So when you do analysis of a column, okay, you need to consider both the axial compressive forces plus bending. And it's actually very difficult. Okay, it's actually very difficult. Okay, so normally what we do then is we use design charts or we use computers. Okay, but in this case, I'm not going to teach you computer lah. Okay, I will teach you the design chart part. Okay, all right. So here in the bottom, we have plan. Okay. So these three pictures at the bottom, A, B, and C, shows the plan view of a column. So imagine if you are looking at a column from, if you're standing in the sky, if you are drone, okay, if you are drone, you use the drone to look down on the building, you're gonna see the column as a rectangular or as a rectangle or square, and you can see beams connecting onto it. Okay, sometimes that column will support 4 beams if it's an internal column. So that will be case A. Okay, if it's internal column, very likely it's going to be supporting beams from 4 directions. Now, sometimes if it's an external column, but not in a corner, then you may see it supporting 3 beams. So in that case, it's not evenly loaded. Yeah. So you compare case A and case B. Case A, you have in the x-axis, you have beams left and right. In the y-axis, you have beams up and down. So the load is balanced. So it's only carrying axial load. Now, when you go to case B, you see the beam at the top is gone. So you actually, now the load is not very balanced. Because the beam at the top is gone, no more beam, right? So because of this, make the beam at the bottom will cause bending. Okay. Now, sometimes, especially in the corner of a building, if you have a column in the corner of the building, so quite often what you're gonna get is you only have 2 beams, rather than 4 or 3 beams. You only have 2 beams connected to your column. Okay. So under this condition, okay, you have what's called biaxial bending. So in this case, you can see you only have so in this case, there's only 2 beams left. Okay, especially corner in a column in a corner of a building. Okay. So the beam at the bottom, there's no beam to counter it at the top, so it's gonna cause bending in that direction. And then there's a beam on the left, which is not balanced by a beam on the right. So it's going to cause bending in that direction as well. So you get bending in both axes now. Okay. So this is sometimes the worst case for bending. Okay. All right. Okay. So before I can go further, I need to clarify the types of structures. I don't know whether I spoke about this before or not. I don't think so. Okay. Okay. So we need to talk about this because it affects how you design the column. All right. So generally, for all structures, doesn't matter whether it's concrete, doesn't matter whether it's steel, you can generally classify them into these situations. All right. Okay. So types of structures. At first, you can classify it into either braced at the top. You can see bracing and shear wall. Those are braced structures. Okay. So in other words, for a braced structure, that means your column is not resisting any horizontal load. Even though you may have horizontal load on your building, those horizontal loads are transferred to the ground using bracing or using shear wall. Yeah. So these are your braced structure. Okay. So you can see the horizontal forces will go into the ground using either bracing or shear wall. So your column, when you design the column, you don't have to design the column for lateral forces. Okay. Something else will deal with it. Your column don't have to worry about it. Okay. Now, sometimes you have unbraced structure. So this is unbraced structure. You don't see any bracing. So then what happens is your column, you have to design for lateral loads. Yeah. So when you design your column to resist lateral loads, what's going to happen is your columns will start swaying. Okay. So it's going to attract additional moment. All right. So these are unbraced structure. So you have braced and unbraced structure. Okay. Now, for unbraced structure, and even for certain brace structure, you can further reclassify them, okay, or separate them out based on whether it's a sway or non-sway structure. Okay, a sway structure means later on there's a definition for it, but right now I just tell you briefly. Okay, so a sway structure is when the horizontal force pushes the frame so far out such that it starts swaying. And when it sways like this, it attracts additional moment. Okay. Next situation, you have a non-sway structure whereby the horizontal movement is not big enough to cause additional moment. Okay. So that's the difference between sway and non-sway. Okay. So there, I have the definition explain here in text. Okay. So types of structure, you have two types, braced and unbraced. Brace means you have bracing. So the lateral loads are carried by the bracing or shear walls. Unbraced means the horizontal loads are resisted by your column. Okay. So you have to design your column to take the horizontal or lateral forces. Okay. In terms of action, brace structures normally resist axial forces and moments caused by the vertical, permanent, and variable loads only, or actions only. Okay. Now, in an unbraced structure, you have to design for the vertical load as well as the lateral loads. Okay, such as what sort of lateral loads have we got on a building? Normally wind load or earthquake. Okay, so that is the difference between sway and non-sway. Okay, so a non-sway structure is when the horizontal movement in a column causes a moment which is less than 10%. So the additional moment is less than 10% increase. So it's not that much. Then we can consider it as non-sway. However, if the additional moment caused by the horizontal movement is more than 10%, then it's considered a sway structure. Okay. Now, next, loading and moments. Okay, so what sort of loading do we get? Okay, so normally what sort of loads do we get in a column? So if you look at the structure that I circled in red, okay, the structure that I circled in red, that's a side view of a building. Okay, so imagine if you look at a building from the side, okay, that's a side view. So you can see how many stories have we have? 1, 2, 3, 4. We have 4 stories. Okay, there's 4 stories on this building. All right. And each story is carrying 1.35 GK plus 1.5 QK. Okay, so when you design the columns in this building, okay, so you can see here, in a brace structure, normally the critical load is maximum moment plus maximum axial load. So M max is maximum moment, N max is maximum axial load. Okay, so M means moment lah. Okay, N for November is axial load. Okay, so bear this in mind. Don't forget. M for Michael. Yeah, M for Michael is moment. N for November is axial load. Okay, so for a brace structure, normally you design for moment and axial load. Unbraced structure, you have to consider several cases. You cannot just consider one case. Okay, you have to consider a case where you have maximum moment, maximum M, and maximum N. In some cases, you have to consider maximum moment, but minimum axial load. This may be the worst case. Okay, especially when your column gets big. Okay. so back to our building. So if you look at our building, okay, now there are 4 stories. So you can see the top 3 stories. Let me save somewhere that I can delete. Can I save here? Yeah, copy for markup. Later I can delete. Right, okay. Now I can jump in. Right, okay. So quickly, I just want to repeat what I said just now. Now that I can draw here. Please let me annotate. Please. Okay. Hey, still cannot, yeah. Oh, I have to choose a pen. Okay. Too thick. Hey, cannot. How do I control the pen size? No, I don't want text. I don't know how to control pen size. Never mind, bear with me. Okay. Okay. So again, M is moment, N is axial force. Normally compression. Okay. So we look at our example building here. So this building has 4 stories. 1, 2, 3, 4. 4 stories. All right. So when you design the center column, this center column here in the middle, okay, to get maximum axial load, obviously you want to have factored loads on all floors. Yeah. If you have factored load on all floors, then you're gonna get maximum axial load, yeah, onto that column. However, to also get maximum moment, you want to create imbalance in the load. So at the floor that is connected right to the top of the column. So normally when we design column, we don't design. So normally when we design column, we don't design. Is this eraser? I think this is eraser. Yeah, this is eraser. Okay. Now, one thing, when we design column, we don't design that entire column one go. We don't do that. Yeah. What we do is normally when we design columns, you cannot design the whole thing one go. You look at it case by case. You look at it, ideally, you design this. Each floor, the column in each floor, you design separately because the axial load that it's carrying it gets bigger as you go down. It's not going to be the same. Yeah, I'll show you why. Okay, let's say on the 4th floor, 1.35 GK plus 1.5 QK, let's say it causes 100 kilonewton on that floor. This also 100 kilonewton. This also 100 kilonewton. Okay, the bottom floor, you have one side full, one side only GK, no QK. So maybe 75 lah, let's say. Okay, so this is the load on each floor. So in the column, that top column is carrying 100 kilonewton. However, when you go to the column on the 3rd floor, it's actually 100 plus 100. It becomes 200 because it has to carry the floor. It has to carry the 3rd floor and 4th floor together. And then when you go to the column below the 2nd floor, it becomes 300. Because why? It has to carry 2nd, 3rd, and 4th floor. And then the column right at the bottom, it's carrying what? 375. The highest, because it's carrying everything else above. All right, so this is axial load. So axial load, you can see it's different for each column in each floor. So that's why you cannot just design the column in one go. Okay, normally, ideally, you design it separately. Okay, because axial load is different. All right. So each column has to be designed ideally separately. Okay. But in real life, we don't do that. But for this course, we do this. Okay. Just so that you get the theory correct. All right. All right. So you can see an axial load. This is axial load. For each floor, it's different. Okay. Next, I want to talk about moment. This is axial load. Okay. Moment. Okay. Now, in terms of moment, let's say I'm designing this column right at the bottom. Okay. I'm designing this one. Okay. Right at the bottom. Okay. The rest, you also have to design that. But I use this one as an example. Okay, I use this one as an example to explain to you the theory. Okay, so for this column, obviously, you are carrying 4 stories of axial load. Okay, but you also want to get the worst case moment, the highest moment. Now, to get the highest moment, you want to create imbalance. So you can see, to create imbalance, what I've done is, on one side of the column, I factored, yeah. On one side of the column, I have factored GK and QK. On the other side of the column, on the right hand side, I only have GK. Okay, now GK is the dead load. Okay, you cannot remove. Dead load is always there. Okay, but QK, live load, can come and go. So that's why, to get the worst case, you may have to remove QK sometimes to get the highest imbalance load. Okay, so you can see left and right, the load is different. When the load is different, it's going to cause imbalance. Okay, so it's going to cause moment that way. All right, if it's balanced, then there's no imbalance moment. If it's balanced, then there's no extra moment. Okay, but in this case, it's imbalanced, so that's why there's all this extra moment generated by it. Okay, so this will cause the worst case. Okay, any questions so far? But can you understand the theory? So you need to understand this to design your building for your project. All right. Okay, next. So the loading and moments in a column. Okay, so you have axial load on a column. So normally the axial load of the column comes from reaction of your beams and slabs. Okay, now this is provided that your frame is a brace frame. Okay, and the lateral movement, this delta L is the lateral movement of the column, is less than 30%, and there's no cantilever. Okay. The rest you don't need to know. Okay. Okay. Next, now the earlier classification is about building frames, building structural types. Now I want to talk about column types. Now column, there are 2 types as well. Okay, so don't get confused with the earlier one. Earlier one, I'm differentiating between the structural type. This is difference between column types. So there are 2 types of columns as well. Okay, short columns versus slender columns. Okay, so these are 2 types of columns. Okay, now the difference between the 2 is actually the slenderness. It depends on how slender your column is. What is slenderness? In short, slenderness means it's a ratio between your cross-sectional area and the height of the column. Okay, so if let's say we keep the height constant, we keep the height constant. So we keep the height constant. I have 2 columns. There, I have the 2 comparison here. Now, the 2 columns underneath, the height is constant. The height is the same. The column height is the same. So the floor to floor height is the same. Okay, but you can see the column on the left is bigger. The column on the right is smaller. Okay, in terms of cross section. Okay, so the column on the left because it has a bigger cross-section area, it is a shorter, it's considered a short column, not slender. Okay. When you have a thinner column, then it becomes slender. Okay. So whether it's short or whether it's slender depends on the area versus height ratio. Okay. So these two definitions are very important. Okay. Why is it important? Okay, because let's talk about the short column first. Now, short column, obviously, it's big. Okay, it has a big area. It has a big cross-section area. Okay, so therefore, it's less likely to buckle. And it's less likely to sway. Okay, so this P delta effect means the sway effect. Okay. Okay, so the P delta effect is small, so it's less likely to sway. Now, the way it fails is also different. Short columns fail by crushing, so the whole thing crushes. Okay, the whole thing, you press and it crush. Okay, now slender column on the other hand, okay, the area is small, but it's long. Okay, so buckling is very likely. P delta effect can be quite big because it can sway quite a lot because it's slender. And most likely it will fail through buckling. So buckling failure is not crushing failure. So buckling failure means if let's say you take apa tu? Dahan pokok. Okay? Kamu ambil dahan pokok, you break it in half, that is actually a form of buckling failure. Okay? When something breaks in half, that is buckling failure. Crushing means something gets crushed and gets flattened. Okay, so column can fail different ways. The best example probably I can give is polystyrene. Okay, imagine your column is polystyrene. You know polystyrene? Anyone knows what polystyrene is?
Yes.
When you buy TV, laptop probably you don't have polystyrene in the box. But when you buy TV, when you buy refrigerator, when you buy your washing machine, you have the white stuff inside, right? The white stuff. Yeah, that is polystyrene. Okay. Now imagine you have polystyrene. Okay. Now if I have a polystyrene that is short and big, okay, I have a polystyrene that is short and big. I get a very fat guy to stand on it. That polystyrene, how is it going to fail? Kemek kan? Betul? If I apply load onto the very wide and very flat, very short polystyrene, a piece of polystyrene. If I apply a very heavy load on it, how will it fail? Dia akan kemek kan? Kemek means for those who don't know Malay, it gets flattened. Yeah, it gets flattened. You crush it. Yeah, it gets flattened. That is crushing failure. Okay, dia kemek. Now imagine if you have a separate case. Okay. Now I have a polystyrene, but it's smaller, but it's long. I ask someone to stand on it, or I apply some load on it. I press it together. How is this polystyrene going to fail? It will start bending, right? This polystyrene will start bending. Agree? And then it will break in the middle. It will probably break in the middle. Agree?
Yes.
Yeah. Okay. That's the difference. So column. So in a column, it's the same thing. Okay. In a concrete column, it's the same thing. Okay. If you have a short column, it's going to fail by crushing. If you have a slender column, something that is small but long or high, when you apply horizontal load on it, so when you apply vertical load on it, it's going to buckle. Buckle means break in the middle. Okay? So that's the difference I'm trying to highlight. Okay? Okay, next. So all these terms that I explained earlier, okay? So all these terms are actually layman term. Okay? These are all layman term. Now, the technical way to determine whether it's short or whether it's slender is actually this. This is the technical way to check the slenderness ratio. Okay, so to check the slenderness ratio, okay, now to check the slenderness ratio, the first thing you have to do is you have to find your slenderness limit. Okay, so let's say I have the same column, same height of building, and I put a column in. Okay, now the limit may be maybe 15 for one column. Well, limit is the same, doesn't change. Okay, the limit for the column is the same. Okay, but if I make my column big, then the actual slenderness may be only 5. Okay, now actual slenderness is 5. The limit is 15. Therefore, 5 is obviously less than 15. So this column is short. In other words, it's not slender lah. When you say short, that means it's not slender. Okay. Now, if I make the column small, then the slenderness will go up, maybe become 20. Now, 20 is more than 15. Then the column is slender. Okay. So this is the technical definition of short versus slender. Okay. It depends on this. What's the name of this symbol? I forgot. What's the name of this symbol? Lambda ka? Is this lambda?
Yes.
Lambda. Lambda. Okay. Yeah, lambda. All right. All right. Okay. Okay. So it all depends on this. Okay. So for today, I'm going to show to you how you actually calculate this slenderness ratio. Okay. This is what we're going to focus on today. We are not going to design column yet. Before you can design column, you need to know this thing. So we are going to go through this first. Okay. So slenderness ratio. All right. Woo. Get this formula. All right. Slenderness ratio. Now, first, so there are two things you have to calculate. All right. You have to calculate the lambda, which is the actual slenderness of your column, which is what we do here in this slide. And then you also have to learn how to calculate the limit, the slenderness limit, lambda lim. Slenderness limit. Yeah. Sounds like my name, Andrew Lim. Yeah, but this one is lambda lim. All right. Okay, but this one, next slide. Okay. This is the slenderness limit. Okay, next slide. This slide, we focus on the actual slenderness of your column. So it depends on the properties of your column. All right. So to calculate the slenderness ratio of your column, okay, there are 3 wait. 1 second. 1 second. Where's my OneDrive? Okay, never mind. Okay, you listen. Okay, I was gonna try to find a way to share the slide with you, but I can't do it until I close this thing down. So you listen, you understand. After the class, I will share the slide with you. Okay. Then tonight you revise. You try to recall what I went through with you. Okay. So after class, I will share this slide. Right. For now, you listen. You try to take as much notes, or you take picture lah. You take pictures. Okay. All right. So to calculate slenderness ratio, right, you need to know the effective length of your column. Okay. So to calculate slenderness ratio, you need to know this effective length, L naught of your column. Okay. So obviously your column has some sort of a height, L. Okay. Your column has a height, L. Okay. But we cannot simply use that column length for design. Okay. Because your column has beams on top and maybe beams or foundation below. Okay. This L that you use in design actually depends on the stiffness at the top and the stiffness at the bottom, whether it's pinned, whether it's rigid, whether it's monolithic. Okay. You have all sorts of different connections at the top and bottom. Okay. So the length of your column, the design length, the effective length of your column actually depends on the actual type of connection you have at the top and bottom. Okay. So even though your column, so what I mean to say is, come, I can't delete. Okay. So even though your column maybe, I don't know, 6 meters, even though your column may be 6 meters, you cannot use 6 meters for design. You have to find what the effective length is. So the effective length is L naught. It depends on some sort of constant times L. Okay, so you have to, basically what I'm saying is you have to modify your L to get L naught. There's a modification factor you have to multiply it with. To get L naught, your effective length. Okay. So how do you get L naught? Next question. How do you get L naught? Okay. Here comes the interesting part. There are 3 ways. The first method is using Eurocode 2, clause 5.8.3.2. That's one way you can get L naught. Second way, you can calculate L naught using these 2 equations. If your column is in the brace frame, you use equation what? You use this equation. If your column is, so if you braced, you see the word braced, then you use the first equation. If your column is unbraced, then you use the second equation here. Yeah, it's a very long equation. Okay. So that's the second alternative. Okay. So first alternative, the Eurocode 2. So first alternative, you use this clause in Eurocode 2. I will show you later. Second alternative, you use the equation in Eurocode 2. Now, third alternative, you can use tables from BS 8110. Okay, so what is BS 8110? BS 8110 is the old reinforced concrete design code. Okay, before Eurocode 2 came about, we use 8110. Okay, even though it's old, it's still acceptable to use that. Okay, so there are 3 ways to calculate L naught. Okay, I'll go through rough one by one with you. Okay, so we go through the first one first, the general definition method. Okay, next page. There. Okay, so this is the first method. You basically use this diagram. Okay, to determine the L naught. Okay, now you have 1, 2, 3, 4, 5, 6, 7. You have 7 cases. Okay, so based on these 7 cases, you choose which one is the most applicable to your column lah. Okay, now if your column is pin at the top, there you can see pin top, pin bottom, then you use the first one. L0 equals to L. Okay? Use the first one. L0 equals to L. Okay? Pin, then you use L0 equals to L. So basically, whatever your column length is the L0 as well. Okay? Second, if your column is cantilever, see, the second one, there's no support at the top. Yeah? It's a cantilever. It's a cantilever column. Okay? So if it cantilevers, then L0 is 2 times L. So you double the column length if it's cantilever. Okay? Now, the third case, if your column is fixed at the bottom, but pin at the top. Yeah? Fixed at the bottom, pin at the top, then L0 is 0.7 L. And so forth. Okay. The next one is fixed. Okay. D is fixed. Then it's L over 2. Now, the fifth one, E, case E, where L0 is equals to L, L is where you have fixed at the bottom, but horizontal roller at the top. Yeah. It can move left, right. Okay. It can move left, right, but it's pinned. It's pinned vertically, but it's roller. It's allowed to roll horizontally. Okay, then L0 is equal to L. Okay, and so on and so forth. All right. So this is the first method that you can use to calculate L0. Now, second method. I didn't include for second method. Oh, I think I missed a slide for the calculation. Okay. The calculation part I go through tomorrow. Okay. We go through the third, we go straight to the BSA 110, the third method. Okay. So the third method is using BSA 110 table. All right. So the A110 table also depends on whether it's a brace or unbraced column, and it also depends on the condition, top and bottom condition. Yeah. So very similar to the Eurocode one. Okay. It looks at the condition at the top, condition at the bottom. Okay. Say, well, if let's say I use brace column, we have a brace column. Okay. So brace column, then we use this first table, then you look at the condition of your column, top and bottom. Okay. So at the top, you have three choices, 1, 2, 3. At the bottom, you also have 3 choices, 1, 2, 3. Okay. So depending on the end condition, you choose a modification factor. You choose a modification factor. So the formula is the same. L0 is a modification factor times your column length. Okay. Okay. So what are the end conditions? There. Condition 1 is where the column is monolithically connected to beams on either side, and which is at least as deep as big as. So basically, if the beams connected to the column is as big as the column, okay, then you have condition 1. Condition 2 is where your column is connected to beams on either side, but the beams are smaller than your column. Then it's condition 2. Okay. Next is condition 3. Condition 3 is where your beam is not monolithically connected to the column, but rather it's pinned. Okay. So the difference between 1, 2, 3 is 1 is monolithic, means it's fixed. Okay. Monolithic means it's fixed, fixed connection. Monolithic means fixed. Okay. So condition 1 and 2 are both fixed connection, but the difference between the two is if the column is as big as the beam, then it's 1. If the column is bigger than the beam, then it's condition 2. Condition 3, if the connection is not fixed but pin, then it's condition 3. Okay, and then you have condition 4 as well, but condition 4 not that common. Okay, condition 4 only applies to unbraced column. There, unbraced column, you have condition 4. Okay, braced column, you don't have condition 4. Okay. Okay. Okay, for this one, I think I start tomorrow. Okay. I'll go through this with you tomorrow. Okay. Give me a second. Let me do the attendance quickly. Okay. Okay, I'm just sharing the attendance QR now. Make sure you scan and yep. Okay, you can do your attendance QR now. All right. So once you've done the attendance, you can leave. You can leave the Gmeet meeting, and I will see you tomorrow face to face. So tomorrow's class will be face to face at the usual place. All right.
Thank you, Doctor.
All right. Thank you. Bye.
Thank you, Doctor.
All right.
Thank you, Doctor.
Thank you, Doctor.
All right. Thank you. Yes.
Thank you,
Thank you, Doctor.
Okay.
Mana ni? Kenapa ni tidak
Thank you, Doctor. Thank you, Doctor.
dapat kan?
Dapat.
Right, thank you, Doctor. See you tomorrow.
Thank you, Doctor.